In example 13, we have yet another example to discuss how we can prove that a series is a geometric series. Now recall that when we want to prove that a series, when we want to show that a series is a geometric series, when we are given the sum of the first n term of a series, here they didn't mention whether it's GP or AP, we are given that sum of the first n terms of a series is given by this. So we have this. Therefore, we are asked to find by finding an expression for the nth term of the series. So by finding an expression for u subscript n, show that this is a geometric series. Meaning they will want us to show that the nth term divided by the n minus 1 term is a constant. We need to state the value of the first term and the common ratio. So, as hinted by the question, we know we need to use the relationship that the nth term is sum of the first n terms subtract the sum of the first n minus 1 terms. Over here, the tricky part is in manipulating the indices. First, let us discuss what the sum to n minus 1 term mean. From the expression for sum to n term, we replace n by n minus 1, so we will have this. So we will have 6 minus 2 power n over 3 power n minus 2. So when we have sum to n term minus sum to n minus 1 term, we will have 6 minus 2 power n plus 1 over 3 power n minus 1 subtract 6 minus 2 power n over 3 power n minus 2. Removing the bracket and simplifying, we will find that we have this expression. Now, to simplify this, it is easier if we express all the powers to n. So we unpack 2 power n plus 1 as 2 multiplied to 2 power n. 3 power n minus 1, we unpacked it to 3 power n divided by 3. 3 power n minus 2, we unpack it to 3 power n divided by 3 squared, so it's 3 power n divided by 9. From here, we see that for us to simplify further, we actually can see that when we multiply out 2 into 2 power n, when we divide by 3 power n over 3, for example, we know that we are going to get 2 into 2 power n times 3 over 3 power n. These 2 and these 3 will multiply together to give us 6. Numerator, we have 2 power n, and this 3 power n will go to the denominator. That's why we will end up with this term here. Now, the manipulation for the second term here is quite similar, and we'll get this. Now, next, for the next line, what we see is this term 2 power n over 3 power n, and this term, they are the same. So we actually have 9 of this, subtract 6 of this, that give 3 of this. And that's why we can have this result. Now, if this is the n term, so we need the n minus 1 term to prove the GP. For the n minus 1 term, we know we replace n by n minus 1. Therefore, the n minus 1 term will have to be this. Can you see? So when we simplify the result of nth term dividing by n minus 1 term, which is what we are having over here, when we have n term divided by the n minus 1 term, what we end up having is the 3 and the 3 will cancel off, and for this 2/3 power n divided 2/3 power n minus 1, we know through indices rule that we will end up with 2/3 power n subtract n minus 1, so we will end up with 2/3 power positive 1. That's how we can get 2/3 here. And 2/3 is a constant because we observe that there isn't any n multiplied to it or added to it, so it is a constant, and we will have proven that the series is a GP. However, remember that we are asked to state the first term and the common ratio. So from this result here, we know that 2/3 is our common ratio, and to get the first term, we need to get back to our result for the nth term here, substitute in n equals to 1. So when we substitute in n equals to 1 in order to get the first term u1, we find that our u1 has to be 3 times 2/3 power 1. That gives us 2. And the result is shown in the last line here. And we state that the common ratio is 2/3. That's the end of the example. Thank you.